The equivalency of roots, a quadratic and a trigonometric function. This is going to be a particular example that I will cover. So, without further ado, let us begin. Start off with a definition. What is a cosine function? The cosine function is a trigonometric function derived from the relation between the side lengths of a right triangle. Let's recall that a right triangle has at least one 90-degree angle. Given the right triangle ABC with sides lowercase abc, let's denote an arbitrary angle BAC by theta, the Greek letter. Now, cosine of theta is the adjacent divided by the hypotenuse, which will be represented as A and C respectively. So cosine theta equals to A divided by C. Now here we have another function, sine theta, which is equal to the opposite of that angle, which is B, divided by the hypotenuse, which is C. And we have one more function, the tangent of theta, which is the opposite over the adjacent, which would be B divided by A. Now here we're mainly interested in cosine and sine functions. Let's talk about the Pythagorean identity. Let's recall the Pythagorean identity is a particular case of the law of cosines, where c squared is equal to a squared plus b squared minus 2 times ab times cosine the angle between them, represented by gamma. Okay, so if gamma has a value of 90 degrees, then the cosine of 90 is 0, so 2 times a times b times 0 is 0. So we have c squared is equal to a squared plus b squared, where c squared is the hypotenuse and a and b are the legs. Now, if we can divide by c squared on both sides, we have 1 is equal to a squared over c squared plus b squared over c squared. Now we can rewrite this as a over c times a over c, which is a over c squared, plus b over c times b over c, which is b over c squared, right? But that's exactly cosine squared theta plus sine squared theta. So we reduce this to 1 is equal to cosine squared plus sine squared theta. Okay. So what is the double angle identity? Let's recall the sum of the angles for cosine function. Cosine alpha plus minus beta is equal to cosine alpha times cosine beta minus plus sine alpha sine beta. Now, if we take alpha equal to beta, and let's just consider the case of alpha, then we have cosine 2 alpha equal to cosine square alpha minus sine square alpha. Why is this useful? Well, we can solve for cosine squared and try and rewrite sine squared in terms of cosine, and then we have a way to reduce cosine squared to cosine 2 alpha, so we can reduce the order. This is going to be helpful if we have a polynomial of higher order in terms of cosine. Okay, let's look at the equivalency of roots. Let's consider the double angle identity, cosine 2x equal to cosine square x minus sine square x. Okay, now we can add 1 to the left side, but we can also add sine squared plus cosine squared to the other side. The reason why is because they're both equivalent by the Pythagorean identity. Alright, so we have the sine squares are going to cancel. We have 2 cosine squared on the right hand side. Then we could divide by 2 and then take square root. But remember, you got to have that plus minus. So we have a way to rewrite cosine x in terms of cosine 2x. Cosine x equals plus minus square root 1 plus cosine 2x over 2. This is going to be useful. If we square both sides, then we have cosine square x equal to 1 plus cosine 2x over 2. Right? So we have a way of reducing the order of a cosine polynomial. Let's consider the following quadratic equation: a times cosine square x plus b times cosine x plus c equal to 0. And we want to form a quadratic whose roots are identical as the following: a times cosine squared 2x plus b times cosine 2x plus c equal to 0. And we want to find the solution for particular values of a equal to 4, b equal to 2, and c equal to -1. How are we going to do this? Well, what we want to do is we want to substitute cosine in terms of cosine 2x and find the conditions where the first equation and second equation are equivalent. After we plug in the trigonometric identity, we have the following. A over 2 times 1 plus cosine 2x plus b over root 2 times 1 plus cosine 2x, taking the square root of that, plus c equal to 0. Now, we also have the possibility that we have a minus, because if we substitute, remember that cosine x is equal to plus or minus square root 1 plus cosine 2x over 2. So it could also be negative. So either 1.1 is correct or 1.2 is correct. Both are possibilities, but what we can do is we can take the product of 1.1 and 1.2. Let's simplify some notation by taking some arbitrary Greek letters, alpha, beta, and gamma. So if we have the product of these two terms, alpha plus beta plus gamma times alpha minus beta plus gamma, well, we're going to have some cancellation of alpha times beta terms. So we're left with alpha squared minus beta squared plus gamma squared plus 2 alpha gamma. Okay, so we're left with this messy equation at the bottom, but we can substitute the values of a, b, and c to reduce it. When plugging in a equal to 4, b equal to 2, c equal to -1, we have the following. 16 times cosine squared 2x plus 32 minus 16 minus 8 times cosine 2x plus 16 minus 8 plus 4 minus 16 equal to 0. Remember, we want to solve for the roots of this. We're left with 4 times cosine squared 2x plus 2 times cosine 2x minus 1 equal to 0. Okay. Now let's pay attention though. We had a equal to 4, b equal to 2, c equal to -1. We plug in these values for the original equation, and it turns out we have the same equation. The only difference is the arguments of the trigonometric function. So we have cosine 2x versus cosine x, right? So we have the same roots of the quadratic, just different arguments. We just need to find the value of x. Since the trigonometric functions are periodic, specifically cosine with 2n pi periodic, then we must have the first solution set consisting of 2 values, because the polynomials of degree 2, right? So we have cosine 2x1 and cosine 2x2, and likewise for the second solution set, cosine x1 and cosine x2, they both have cardinality of 2. Okay, so we have two possible cases. 2x1 equal to plus or minus x1, and 2x2 equal to 2 plus minus x2, right? So the second case is 2x1 equal to plus minus x2 and 2x2 equal to plus minus x1. Okay, so you may be asking, why do we have the plus minus? The reason why is because cosine is an even function. So let's explore these possibilities. In the first case, we have the following. 2x1 equal to plus or minus x1 plus 2n pi. Now, if x1 is negative, then we can add x1, which is 3x1, divide by 3, so we have x1 is 2n pi over 3. If it's positive, then we subtract x1, we're left with x1 equal to 2n pi. Alright, so we just need to plug in the values and see which one gives us the solution to 0. So for cosine squared 2n pi plus 2 times cosine 2n pi minus 1, here we have, remember that cosine of any integer multiple of 2n pi is the value of 1, right? So 4 times 1 plus 2 times 1 is 6 minus 1, which is 5, which is non-zero. Now in the second case, we just substitute with 2n pi over 3, right? So n could be 0, right? Which would give us the same equation as the first. It could be 1, which would give us a value of -1/2. It could be 2, which is also a value of -1/2, right? So we have 4 times -1/2 squared, which is just 4 times 1/4, which is 1, plus 2 times -1/2, which is just -1, right? So 1 minus 1 is 0, minus 1 is -1, which is non-zero. Okay, so those two didn't work. So the first case didn't work, so we go with the second case. In the second case, we have 2x1 equals to plus minus x2 plus 2n pi. Okay, so this is x1 written in terms of x2, right? So we need to find x2. But what we can do, we knew that 2x2 is equal to plus minus x1 plus 2n pi. We can multiply both sides by 2. So we have 4x2 is equal to plus minus 2x1 plus 4n pi. 4n pi is the same thing as 2n pi because n is arbitrary integer, right? And the period is 2 pi of cosine. Now, we can just rewrite 2x1 as plus minus x2 plus 2n pi, right? And here we just have 2 plus or minus. It's not much of a difference because n is arbitrary integer. So here x2, if we do some reduction, we have 2n pi over 3, which is the same as the first case, and we also have 2n pi over 5. Okay. So if we have negative, for instance, right, then we have 4x2 is equal to negative x2 plus 2n pi, right? We just add x2 to the other side, so we have 5x2 is equal to 2n pi, and then we just divide by 5, so x2 is 2n pi over 5. So then we have 4 cosine squared 2n pi over 5 plus 2 times cosine 2n pi over 5 minus 1. Right? And actually, even though it's not on the unit circle, if we plug this in using a scientific calculator, we do have a value of 0. So our solution is x2 is 2n pi over 5. And we just plug it in to get x1 here. And we have our solution. So that concludes the problem. Thanks for watching, and remember to like, comment, and subscribe.